Okay, hey. So this is what I've been thinking about doing um, this week. A little sort of virtual machine, little virtual computer platform. I thought it would be fun to have something that is sort of both a learning project to build one of these things, and also something that can be sort of a substrate or um, uh, sort of a little foundation or something like that for other hobby programming languages. I've put together a couple of compilers and languages and stuff like that in the past, and I think you always come to this point where you either need to go reach for LLVM, which is obviously a huge chunk of code to include, and complex dependencies and stuff you're including to generate code for any type of machine, right? Or you can go with something and say like, well, I'm only going to generate code for this specific thing, and there are other options like binarian and stuff like that for WASM. And a few times I've attempted to write my own, IR, and also a few times my own machine code generator. And that stuff obviously is just like very complicated, really time-consuming task. And sometimes that's fun, sometimes that's for learning how that stuff works. But other times they just want something that's running. So that's one of the goals. So it could be kind of nice if this little thing could be an escape hatch for the times I want to create a little hobby programming language and just kind of want to run it on some machine. So generating code for this should be pretty straightforward. And from the first goal, like just having fun and learning, I think simplicity is pretty important, because it's a limited amount of time I'm gonna spend on this. And third, I think that computers are just sort of moving very quickly. There's some weird connection to sort of consumerism in the way we write software, right? There's this sort of, write it, ship it, run it, and then we just move on to the next thing. And the thing that we just shipped, it's dead, right? Even the web is something where you constantly have to maintain your program for it to keep, or your web page or whatever, for it to keep like working, right? If you just build something, you put it on a web page, and you wait a few years, it'll just be broken, right? Unless you use a very small subset of the web platform. And that's kind of natural, right? I think that comes from some of the origins of web, and some of the that there's no versioning, right? There's no different versions of the API and stuff like that, and also the fact that it serves a huge economy of use, like software and stuff like that, right? And then of course we have specific kind of operating systems or platforms like Mac OS, Mac OS 10, Mac OS 11, Mac OS 12, Windows 10, Windows 95, Windows 11, a variety of Linuxes and BSDs, yeah, obviously you can write a program. I think Linux is probably the thing that gets the closest to me of all the options right now. If you only consider the Linux kernel, which obviously gives you a very limited sort of way to express yourself, but if you only go with the Linux kernel, you have sort of the syscalls, which is kind of like a virtual machine in a way, if you bend it a little bit in your mind. And that's pretty much stable. You can run a thing that was written in the 90s essentially on like a kernel from yesterday. But obviously, as soon as you include third-party libraries, like those things are gonna change, and you're gonna be back in this kind of thing. Anyhow, I digress. Long side conversation, interesting about that. Anyhow, I think the third point would be, and maybe I should take these out. So a couple of little goals. So first off, learn, have fun, right? So simplicity. The second point I was talking about is some sort of substrate. If I can spell. Oh, there we go. Some sort of substrate thing to make other things on. Okay. And the third point, which kind of talked about a lot, is I wouldn't say perma-computing, but sort of longevity of programs, maybe longevity. Sort of, you know, I want to be able to run a program, a multimedia. Or is it just multimedia? Is that how it's called? Program in 10 plus years. Right. And that was interesting. Like looking at things like Nintendo, right? NES and SNES, Game Boy. There's like a whole bunch of these, like, you know, C80 things. C64, there's a bunch of these systems from the past that were really simple that people are still building programs for today and emulators. And that's probably the closest we've gotten, I think, to something that's somewhat of a longer life, right? I don't think anything is permanent. Everything is transient, you know, if you want to be philosophical about it. But so I wouldn't go as far as calling something permanent or permanence. Anyhow, that's Stadium. And here we have a couple of other notes. I shared these on the Twitter the other day. I think I did at least. Well, I think that this thing, whatever it is, she just embraced the linear memory model. You know, this idea that that C embraces WebAssembly, for example, many things, right? This idea that there might be on actual hardware, you know, multiple sort of segmented memory models and stuff, but let's just say that memory starts at 0 and it ends at some sort of like large number, right? And the way you address things is by, you know, giving it an offset, right, from the 0. Pretty straightforward, proven, simple, really flexible model. So let's go with that. Rather than anything high level that's like, oh, memory is just the concept, man. Now, let's just, you know, put like an address in a register or whatever we'll end up using, and just treat that as a number, treat that as an address. Just do pointer arithmetic and stuff like that. That stuff, I think, sometimes people are like shying away from that in C or saying that's the root of a lot of bugs. And yeah, sure, that might be true, but I think that is also the root of a lot of the awesomeness of something like C. Okay. Simple semantics. There should probably just be. Actually, I think I've changed my mind about this a little bit. That there should probably just be like global constants as a concept. Like there's just constant data you can bake into a ROM or executable, whatever you call that, like a little program. And then you can reference those constants, right? So if you want to have like the, you know, constants for pi or something like that, you can just bake that into your program and then you reference that in all the different functions. There's some constant mutable locals, and that includes parameters and variables. I think those are all treated the same. So inputs to functions, outputs from functions, and temporary sort of like variable data inside a function are all the same thing. And then there are conventions around like, you know, in how do you provide the parameters before a function call? How do you read the results after a function call? I think that the virtual machine should use registers because I think that's just like a really neat ES model. I just kind of like that. Stack models are cool too, but I think it would be more of a fun challenge to go with registers. But there might be a little like I'll get to that in a minute here, but there might be a little sort of like layer on top, a very, very lightweight, tiny sort of assembler / compiler that might allow you to say, hey, you know, just call this thing X and go pick a register for it later automatically for me. I don't want to pick registers. I think that would be neat. That would just make a bunch of stuff like easier to do. Essentially, when you don't care about a register for temporaries, which I think is the majority of cases, you can just give them usable names. And finally, some sort of simple syntax, and this is about the little input language, which I won't start with writing this. This would probably come a little later, but some sort of simple syntax that is really easy to parse and read. And so here's like, here's some sort of little idea. Obviously I'm playing with the syntax and this doesn't, mean much. But semantically, like there's this idea that you have a local, right? So one of these things, like a register essentially, but you can name it. So you say 1, and then you say 1 is like number 1, which would be a constant, a global constant that you reference here. So this will just simplify that for you. And then you say 2, and it's like load the other global constant, which would be number 2. And then you say something like, in this third register, put the result of adding this register and that register together, right? And then put the result of that into, this is weird. She has to, and return the result of that in result value 1, something like that. So that's the general idea. Let's see. Then I shared this on Twitter, I think 2 days ago. So the next thing I started playing with, like, what is the level at which you are deciding on where things going, where you're putting these little programs together as text, as source code, not the VM instruction set. I'll get to that a little later, but and I think that there are 3 options. There's a register style, right, where you're explicitly naming your registers. You're explicitly storing, loading into memory and from memory. There is an SSA style. This is usually what you find in like most compilers' intermediate representations. Like if you've ever looked at LLVM's IR, for example, it will look roughly like this. SSA, I guess, like, sorry, let me just mention the last one. The last one is like local style. And this is what you'll find in things like, I think this is more common with stack machines. You'll find this, but both WebAssembly and Lua uses this kind of abstraction. I guess Lua got kind of registers, so they call them that, but yeah. Anyhow, I think what SSA brings, cons and pros compared to register style, is that you have this kind of like named values, right, rather than you explicitly defined registers. You then though have to deal with like FIs, which are essentially like a kind of a fan-in thing. If you're familiar with this, you know what this is, but if you're not, FI is essentially it's like, let's see, what's a good metaphor for this? Okay, let's say that there are 3 doors in front of you, right? And your friend now goes away somewhere around the house, and then comes back to you out through door number 1, right? And then the friend goes around again, goes through the house, and come out through door number 3, right? And maybe the friend is bringing different, like, I don't know, treats or something, like a cupcake when they come out of, door number 1, and maybe like they have eaten the cupcake when they come out through door number 3. And so for you to be able to like know what, shit, I don't know how to phrase this. Anyhow, so phi is essentially saying that, this person can come out of these 3 different doors, right? And whatever the number of cupcakes is going to be whichever door they came out of, right? So in this little case, you have result 1 here. So when you get to this block, so you go, it goes 1, 2, 3, 4 like this. So we start here, and this just says you just jump to block 1, right? So it just continues. This thing will be important later. Actually, this is dumb. I think you can skip this. Anyhow, and the first thing it does is says like if it comes from door, block number 0, then the value is 1. But if it comes from door number 3, right, block 2, which comes down here, then the value of res 1 is the value of res 2. And you can have more things if you have more predecessors. And the same thing is here. Anyhow, it gets a little complicated. Just explaining it is a little complicated. Once you grokify, it's not that hard of a concept, but it definitely does complicate things a little bit logically. For example, you have to sort of like, as you're writing this, you sort of have to have the premonition or the foresight to see that you're going to write this block down here, and that's going to become a predecessor of annotated predecessors here on the side. Anyhow, I rolled this up pretty quickly. I think this is something that is really useful, especially for optimizations. SSA is useful, sort of as an intermediate, but not as something that you write. I think either like kind of traditional assembly with when you name the specific registers, or the local style. And I think the local style is the best one. So actually, I think we ended up with a combination of both of these. So for the virtual machine, it explicitly names registers. There's no concept of locals in the virtual machine. But as you're writing these little programs that little thing will put together into virtual machine programs, you do deal with locals, and then the registers are allocated for you automatically when this text is parsed and compiled into VM bytecodes, opcodes. Okay. So that's the deal. You write this, and this is kind of what it looks like on the inside. Okay. I did some explanations here, but I'm not going to talk about these. I think these are some things that also made me excited about just the concept of things, like to be able to write programs at this level that can draw to the screen, they can play sound and stuff like that without having to involve any particular operating system concepts. Again, to satisfy longevity and substrate points for the goals. Okay, so yesterday I was sketching out a little bit of what the instruction. I got a weird code. What the instruction encoding might look like. I think Lua has a pretty elegant yet maybe slightly over-engineered. I don't know. No, actually, I would say it's pretty elegant. It's pretty nice. Instruction encoding. And what I ended up with is something very similar to Lua, which is where do I have it? Here. So as you might have noticed, I've put together a really simple program here. Let's see, put my coffee cup away. If you look at the code, it's pretty little. Just some stuff I put together to get started. And let's see. Build. Debug. I forgot about this. Run. Where's it gonna end up? RSM. Okay. I just have this little build script that it just generates. Maybe I should tell you. So there's the magic. It just generates like a Ninja build file, and then it just runs Ninja essentially. So to keep this super minimal, the only dependency here is bash and Ninja, and obviously a compiler. I'm using Clang. Okay, so build it, run it. This program right now doesn't do much. Maybe I'll get to this in a few minutes. But let's just look at this first. Okay, yeah, let me just clear this. Okay, so instruction encoding. I also looked at RISC-V. RISC-V is obviously pretty cool. And yeah, there's a bunch of other architectures that are interesting and neat and stuff like that, and elegant in various ways. I think what I've done here is ended up in a place where I was like, oh, can I pack these bits together? Really? Like, I probably only need 7 bits for like the operation code, right? And maybe I can even get away with 6 bits. Like 64 operations seems fine and stuff like that. And I tried to be really clever about it, and I was like, you know what? That's ridiculous. So let's just keep it simple. The each instruction is a fixed size, and that allows some cool things, like the PC can be instructions, and jump offsets and branch offsets and stuff are instruction counts. And that means that you can just make it so that memory addresses is always like data memory. There's no executable memory that you deal with. You only deal with like instructions and instruction distances, right? And that might make code more portable. So they're 32-bit long. They're a little endian. This I just kind of mentioned this line here, that they're expressed in instructions rather than bytes, and then I give the what is this? Is this most significant? I always forget about this. I have to like go look this up now. I feel like dumb. Okay, whatever this is, least or most. I think it's most significant, right? Anyhow, I believe this is the most significant bits. These bad boys, these first 8 bits, I give those to an opcode. So RISC-V and Lua, for example, has like a smaller opcode field. It's got 7. It used to have 6. It's got 7 bits now, and then it's got 1 bit like that squishes in here that they call K. Which is sort of like a flag that like changes slightly the meaning of the arguments for the operator or the operation. And then I don't know if I'm right here, but I think that's sort of like a bit of an afterthought, realizing that like, well, we should have like a move operation for like register to register, and a separate move operation for a constant to register. But instead, this K flag indicates if, like, the B immediate names a constant, names a register, and it gets a little complicated. And similarly, like RISC-V has what they call func, like 3 and 7. I don't know why they're called 3 and 7, but they have these 1 or 2 different fields in the instruction that comes with the operation. So, like, I think now I might be wrong. I have the RISC-V. I hope you can see this. Let me bring this into the viewport. Yeah, let's see. All right. Where is it? Base instruction format. It's here somewhere. Okay, here we go. So this is kind of what RISC-V does, which makes it a little tricky. Like, there's the opcode, 6 bits. So 64 of those, right? Yeah. Make sure I'm not insane. And then you got this thing here, func3, func7. So that this thing actually, like, together with this, describes the actual operation to perform. Right, so there's some examples. Maybe integer, I'm just going up to, okay. Yeah, so for instance, here are some, this will do, right? So here's like an opcode called operation immediate, maybe, I don't know. And then in func3, you have this like secondary opcode that's like add an integer, or, there's other operations, right? So essentially, like, what they could have done here, and I'm sure they have really good reasons, and RISC-V is like, a real industry strength architecture, but I think semantically, at least, you could say that this is really just like an opcode that's called add I immediate, right? If you smash those together. So So I was thinking, this is just a hobby project. I'm not going to make it very complicated. I'm not going to try to make it like the most performant thing or anything like that. So let's just have, for anything like that, like where you have a move from, constant to register, let's just make those different opcodes and make the opcode field large enough to fit a bunch of operations. So 256, probably more than what I'll ever need for something like this. The remainder of the instruction encoding is just a bunch of fields. So like for things that need 4 arguments, there is 5 bits for slot A, 5 for B, C, and then the remaining bits 9 is for a 4th slot. And then as like you only need 3 arguments, then the third argument then is like a wide one, and I just choose W here, inspired by Lua's like naming scheme. I think they call it K or D. I don't know. They call it some letter. I didn't know what it was. I was like, well, it's wide, so let's use W. So that's what this little nomenclature in here means. That the third argument here now is like sort of a wide one. So for stuff like immediate values, you now have like 14 bits instead of 5 bits, right, to express something. So if you have something like a conditional branch, then 2 to 14 is going to give you like 16,000 possible like instructions that you can skip forward to, right? Or I guess 8,000. That's more reasonable because it would be a signed number. So it would give you 8,000 instructions that you can jump forward to or backward from. This is just an example of like an immediate, like a branch instruction with an immediate value of like how many do you jump to. For one that uses like a register as the indirection, you can just use this. So the registers, there are 32 registers for each type for integers and floats. 5 bits is enough to express 32. And yeah, so you can see this picture, what happens if you only need, one single argument, you have 24 bits, and now suddenly you can express really large numbers. Okie dokes. So then, what I've done here in this project is I've set up a couple of macros just to like make this encoding stuff less of a headache. This I took from, let's see, this other, I'm just gonna lift this over to show. This is from a different project. I put together this hobby VM many years ago called Sol, which in turn was inspired by Lua. So I have retrofitted these macros into this new project. So you can see I've just put here like sort of like the size of the operation, 8 bits, of the arguments A, B, C, and D, and then sort of like what is the size of, when the D argument is not used, what is the size of C and B and A and so forth, and then the position of them, which is just, it's going from this direction into this direction. Since you have the most significant. Sorry, I have to look this up. I'm going crazy. Yep, on my phone. Why is this so hard to figure out? Mostly within bit little endian. Let's see. See, stuff like this, I learn about it when I need it, and then it goes in here, it stays when I need it, and it goes out, and I forget about it. Some dumb Medium article. Just gonna look at it. Okay, you know what? I'm not getting boring with this stuff. I'll figure this out later. It really doesn't matter. I just want to call it a thing, over here. Okay, so this is kind of just what I put together this morning. I've got just some code I retrofitted from a previous project. This is just a super simple memory allocator. It just grabs, it just does memmap, just grab a chunk of bytes, and then it just, hands them out essentially. And then a super simple just array implementation. And then this file just has, I've just generated a list of names of the operations and the types that the header file has defined, just to make things easier to print. And the header file here, I just made a list of the types. I think there are really only a few types. So the register size is 64 bits, at least I think that's what I'll stick with. And that means that there are 5 sizes of integers. 1 bit, for bool essentially, and then there are 2 size floating point, and then this, I think I might just get rid of this. This doesn't really, I don't know, I just toss it in there to play around, but a pointer type. But I don't think there will be pointers as in like executable memory pointer distances or anything. That will not be needed. Let's use an i64. And then just like a few operations. I just wanted to plug a couple of these in just to figure out if this was like sensible. And then I have just a couple of type depths, like the type code. This is just this thing, right? Is like 8 byte. And then just like generate an enum for that. And similarly, the opcode is like a byte. Fits in here, and generate an enum for those, and then just say that an instruction is U32, right? Unsigned 32-bit integer, and then here is just a little structure for the memory allocator that I show you, a little structure for an array, the 2 function definitions for getting the name of an operation for like printing and debugging and stuff like that. And then a few routines here just for the memory manager. Don't have to like look at those. It's just run of the mill stuff. A function for growing an array. And then this thing, I tossed this in. I'm pretty sure I'm gonna need it because I need this in pretty much every project. Let's see. Oh, I didn't name this. So this thing is essentially just like a append buffer, just for doing things like string formatting. Basically always need something like that in projects. Yeah, so that's it. So there really is no code yet. There's just some definitions of types and operations, and surely I will be changing this, and definitely be changing this list of operations here. And then the program itself. Right, I showed you these kind of macros. That it looks kind of nasty, but it's just sort of shifts and ors and ands. Okay, and finally here, I'm trying to just put together this factorial example program that I showed you from in the idea file. Okay, so earlier I was talking about thinking about should the style of the VM and or the style of the assembly format that you write as a person deal directly with the registers. Should it deal with SSA name values or sort of locals, variables? Anyhow, so I grabbed this and I just pasted it in here in a comment. And then I recreated it here with the operations, right? So rup_move is just this thing here, right? And that's just generated with a preprocessor macro here to become, rup name. And then we have the arguments. So this little macro here, maybe I should grab this down here so we can look at this table. So I'll slot that in here. I made my screen a little smaller so it fits on a video thing. Leave it out here, put it out. Okay. Squish this in. Yeah, perfect. Okay. So the first thing, excuse me, it's a little coffee. The first thing that happens is that we're copying register 0, which is the first argument, which is the number we want to factorize. So we copy this into register 8. So this is just a temporary. You can see this light up here in my editor. This is just temporary. And we make this copy. This is just the implementation of factorial. It's nothing to do with the VM, but we just do this to simplify the return value, since in this hobby ISA here and my hobby calling convention, isn't this my idea program thing here? Okay. Let's see. Oh yeah, separate file. Yeah, so there's a little calling convention here that the first 8 integer registers are both inputs and outputs to a function. Same for a floating point, right? So jumping back here, that means that this function has one input parameter and one output result, right? And that means that this guy is in R0, and this guy is also in R0, so I read this as 0. And factorial, and at least this tail recursive version of factorial, just accumulates like a result. So we're using R8 as the accumulator, and we just initialize that to n. And then we're going to use this other register to just get a return value, and that way we don't have to do an extra copy and stuff at the end. You can write this probably many ways. Also, I have not run this. I don't know if this works. I've just like looked at this and thought about it, so I might have made a mistake here. But I think this function would work if it was compiled. And so that just corresponds to the same thing. 8 here, register 8. That's just this number down here, right? So move, or maybe I should name this copy instead. This annoys me sometimes because it's not really move like what the move instruction does in most ISAs is copy, right? You copy the value in register 0 to register 8. Like after this operation, it's not like register 0, it's like invalid. Now register 8 and register 0 has the same value, so it's more of a copy. But anyhow, so this copies 0 to 8. And an IP here, I don't know if you saw it earlier, this is just like I just allocate a bunch of memory here for like 32 instructions, which is probably more than enough. It is certainly for this program. And so what I do, this is just an array of 32 instructions, right? And then I have a little program counter, right? It starts 0, 0 right here. Starts right here at 0. And then as I add instructions to this array IP, I just increment the logical program counter. Okay. So next thing is just loading an immediate. Right, so this loads the immediate value 1 into register 0. Okay. So into register 0, load 1. I've annotated here on the side. The next thing that happens is a conditional branch. So we want to check in the factorial function. We want to check if the argument is 0, because if it is, we're done and there's nothing to factorize. So we check here if equals, right? So if the value in a register 8 is equal to 0, then branch to end, right? So if n is 0, go to end, and end is down here. So then it just skips all of these things, 3 instructions, and it will issue the return instruction, which ends the function. And the return value will be 1, since we changed that here, right? So you give it 0. Am I wrong about this? I should go look up the factorial function later, but I'm pretty sure. Okay, so branch, I'm just playing with language. If equals, or the more traditional BR for branch, I don't know. So branch if equals immediate. So branch looking at register 8. If it's 0, then branch by jumping 3 instructions forward. So it's a relative branch, right? And 3 instructions. These are the 3 that will be skipped. The next 3, right? And the final one is ret. So if the value in register 8 here is 0, then it's going to increment the program counter by like 3. So we'll do PC 3 here, right? Which when it's evaluating this, which means that it would skip these and then it would resume up with return, right? How most CPUs do it. There's also like probably an absolute branch instruction that this thing should have that says, go to and a specific number of like go to instruction offset 1828, from the very first instruction of the whole program. So you can do absolute jumps and stuff like that. But what I want to do here is just start really small and just see if I can get this really simple function just working, and then work my way out from there, right? So there would be no parser or anything like that for this until this thing works. The next step after getting this together, sorry for scrolling. The next step after getting this thing together, I think will just be a little function that I can give this array of instructions to. That will then just print out the do the opposite essentially of this disassemble it or whatever you want to call it. Print out exactly what they are. I just like to, if I hit save here, you'll see on the right side that save a couple of times. This is just the way I like to work. I like to kind of explore programming and have it sort of like live updating more or less as I'm writing programs. And so right now you see this is the end of it. I just print out the size of the instructions, right? Which is 28 bytes, it says up here. The other stuff is just some printout to tell me what's going on. So it's, when I hit save here, it runs that build script I showed you earlier, which just runs Ninja, the kind of like a make system, really simple. And that just like recompiles any files that have changed and dependencies, links the program, and then the build script just runs the program for me here. So this is just the PID of the program running, so it runs the program. And bytes is a print statement. Where did I print that? Oh, that was like when I was testing out the memory thing earlier. So remove that. Let's go back. Keep it simple. So it just runs this program, right? And here is that log message. Okay, so that's it. That's what's going on here. So for that reason, the next step I want to do, that'll be in another video. But the next step I want to do is to format this so I can get feedback about like how much did I screw up, because I always screw up, I always make some mistakes, and so I want that feedback of like what does the program look like versus what is the encoding I believe I made for the program. So that's gonna be the next step. And after that sort of formatter or debugger or whatever, or not debugger, formatter, let's call it formatter. Will be an evaluator, like the sort of the heart of the virtual machine, the thing that runs this little program and spits out the result of the computation of this function, right? Where we can give it an input value, an input argument, and then we just print out the result from it, and we can and from there is it's a little fussy to tell, but at some point after there will be some parser for writing this sort of little simple assembly language to avoid having to do this kind of compile time program building. Yeah, so that's it. That's the summary. Yeah, let's see what happens. If you're interested in this stuff, just reach out on the Twitter. I've tried to do these like live streams on Twitch before, and it's been just like a very like unpleasant experience. Not from a human, not from an audience perspective, but from like a technology perspective. It's just like super janky stuff, and I'm not gonna do that. But I'll try to do these kind of offline videos, and yeah, you can also reach out on Twitter. Until next time.